Hi, welcome to the next of our series of practical electromagnetics for engineers. Today we're going to be talking about the phase velocity, along with the impedance that we covered in a previous short lecture, one of the two critical parameters of transmission lines. We know that waves move on transmission lines. This is our schematic for a general transmission line with an impedance Z naught. Generally, we know the waves have amplitude for the positive going component, which is in this direction, and the negative going component, which goes in that direction. We have attenuation given by the alpha terms, and we have phase. It turns out that in the lossless case, we can ignore the alpha terms, the parts that are real, so we don't get a decay of the amplitude. Let's look at a simulation, which we've seen in a couple earlier videos, but let's remind ourselves of what these waves really look like as they're varying in both time and space. Okay, you saw from that simulation that the thing is wiggling around, but you definitely see a motion. We showed the motion in the positive direction only, simply to keep things fairly easy. How fast is that wave moving? Because you saw from the simulation you can definitely see a motion. Well, it turns out that the phase, the peaks of the wave, or the troughs of the wave, that's what we call the phase velocity, because those are points of constant phase moving in z. We know velocity is simply given by the change in distance divided by the change in time. We also know from our basic video on waves that the frequency is determined by the change of phase with change in time, and beta is the change in phase with the change in distance. With these definitions, which come from a basic understanding of waves, we can do the following algebra. We basically just take omega divided by beta. We see these phase terms are going to cancel out, and then we simply flip over the time, and we find that omega divided by beta is the phase velocity. So if we're given the frequency and we're given the beta coefficient, we know what the phase velocity is of the wave. It turns out in the lossless case that beta is just omega, the radial frequency, times the square root of the inductance times the capacitance. So if we know the inductance per unit length and the capacitance per unit length, we can find beta. And when we go ahead and plug this into omega over beta, we find that the phase velocity is just 1 over the square root of LC. So along with the impedance, this phase velocity is one of the really basic ways we characterize transmission lines. You'll see it in pretty much all the data sheets on transmission lines. Remember that the speed of light is about 3 times 10 to the 8th meters per second. A good way to remember it is that light travels about 1 foot per nanosecond. So again, where does this phase of velocity come from? Let's do the same trick we did when we looked at impedance and put a step function input into our distributed circuit model, ignoring the resistors and the conductances, and just work with our lossless line here. What you find is that, as you saw before, if you have small inductors, you have rapid changes of current, rapid decays of voltages. Big inductors, slow changes of current and slower decays of voltages. Similarly with capacitors, the smaller the capacitor, the faster the voltage and current will change. Let's see what this looks like for our phase velocity. It turns out that if you have a small inductance and a small capacitance, and we're only looking at the voltage there, so let's cross that current off, you get very rapid changes in the voltage. And it turns out that if L is small and C is small, V phase is very high because that square root of LC is in the denominator. Similarly, if we look at the voltage and how fast it moves on the transmission line, if we have a big capacitance and a big inductance, you see these things change slowly. You get a larger denominator and a slower phase. So you can derive why the phase velocity depends on the inductance and capacitance of the line, because it simply takes longer for the current to charge that capacitance up. It takes longer for things to change when you have a big inductance, and thus the wave moves more slowly.